In this video, we are going to cover conservation of energy with friction. So just remember, mechanical energy is only conserved when there is no friction, but total energy is always conserved. However, you do have to take friction into account. So to calculate what we call the internal energy, you just calculate the work done by friction. So E int, energy internal, is equal to the work done by friction. So let's see how this works in a problem. In this problem, we have a 10 kilogram block is released from point A. The track is frictionless except for the portion between B and C, which has a length of 6 meters. The block travels down the track, hits a spring of force constant K equals 2,250 newtons per meter, and compresses the spring 0.35 meters from its equilibrium position before coming to rest momentarily. Determine the coefficient of kinetic friction between the block and the rough surface between B and C. So as always, we start out conservation of energy problems by analyzing the initial scenario and the final scenario. So our initial scenario is the block being up here, and our final scenario is the block has come to a rest while compressed against this spring. So the initial scenario, we're just going to have gravitational potential energy. In the final scenario, we're actually going to have two types of energy, because right here, there's going to be some internal energy. So it's like thermal energy and sound energy created by friction. And then also in our final scenario, we're going to have elastic potential energy. So this internal energy is considered to be in the final scenario because this internal energy is still in the system when the block hits this point. So we just want to set GPE equal to E int plus EPE. And then we can go ahead and plug in the formulas that we know for those types of energy. So GPE equals mgh, and we know that the internal energy is going to be the work done by friction, and then the elastic potential energy is 1/2 kx squared. So how would we be able to calculate the work done by friction over this 6 meter length? Well, we know that work is equal to force times distance. So it'll be the force of friction times the distance the block goes. Now, how do we calculate this force of friction? Well, we know that the formula for kinetic friction is the coefficient times the normal force, and then this surface is flat, so we can assume that the normal force is equal to mg. So this is what our E int equation turned into once we figured out some of the physics and math of it. Now we can go ahead and plug in our variables. So what are we actually looking for here? Well, we're determining the coefficient. So that means this mu right here is going to be our missing variable. So we should have information for everything else. So m is 10, g is 9.8, h is 3. Again, it's 10, 9.8. D is 6. We're given the spring constant. It's this number right here. And x is the 0.3. So I'm going to move on to the next slide to do the rest of the problem. So at this point, with mu k being our missing variable, we can just solve for that. So 294 equals 588 mu k plus 101.25. Subtract 101.25 from both sides. Then divide both sides by 588. And we get the coefficient is equal to 0.328. So that is one example of how you account for friction. So let's do a slide problem, which are pretty simple when you don't account for friction, but a bit more complicated when you have to account for friction. So a girl slides down a slide with a height of 2.6 meters and a diagonal length of 5.5 meters. If the coefficient of kinetic friction between her clothes and the slide is 0.2, what is her speed at the bottom of the slide? So as always, we account for the types of energy. So at the top of the slide, the girl has gravitational potential energy, and at the bottom of the slide, she'll have kinetic energy and internal energy. So here we just want to set GPE equal to KE plus the internal energy. Then we want to go ahead and plug in the formulas that we know for those types of energy. So again, we know that the internal energy is the work done by friction, and the work is just the force times the distance. And notice that we're given the distance here, it's 5.5, because that's the length of the hypotenuse here of this inclined plane. But we still have to figure out what the force of friction is. So this, we have to think back to some of the stuff we know about forces on inclined planes. So first, we know that the force due to friction is equal to the coefficient times the normal force. Why can't we just go ahead and plug in mg right here? Well, we have to think about what is Fn, the normal force, on an inclined plane. So the normal force is equal to mg cosine theta. So that's why it would be wrong if I just plugged mg right here. But this is kind of a problem. We're not given the angle. But we've got two sides of this triangle, so we can use trigonometry to find this angle. So the sine is equal to opposite over hypotenuse. So that's sine of theta equals 2.6 over 5.5. So theta is going to equal the inverse sine of 2.6 over 5.5. So it is equal to 28.2. So our final little formula that we have here before we can plug in numbers is mgh equals 1/2 mv squared plus mu k mg cosine theta d. So notice that this is convenient. All of the masses cancel. And now we can go ahead and plug in our numbers. So g is 9.8, h is 2.6, v is what we're looking for, mu k is 0.2, g is 9.8. The cosine of the angle, we want to plug in 28.2 for the angle, and d is 5.5. So simplify that a little bit, then subtract 9.499 from both sides, multiply both sides by 2, and then square root both sides, and you'll get that the speed of the girl at the bottom of the slide is 5.65 meters per second. If you calculate what her speed would have been without friction, it turns out to be about 7. So friction, even with this pretty low coefficient, has a big impact on how fast she ends up going. Okay, here is sample problem 3. So it's a roller coaster with friction. So we have a roller coaster cart starts out with a speed of 7 meters per second at point A. The total distance between points A and B is 55 meters. The total distance between points B and C is 30 meters. The total distance between points C and D is 22 meters. So I'm giving you the distance here because we need to account for friction. And the frictional force acting on the roller coaster cart throughout its ride from A to D is equal to 1/5 its weight. Find the cart's speed at points B, C, and D. Let's start this problem by just seeing what type or types of energy are at each point. So at point A, we have gravitational potential energy and kinetic energy. And at point B, we have kinetic energy, but there's friction all along here, so there's also going to be some internal energy. So I'm going to call that the internal energy between A and B. Now, at this point, there's a couple different ways you can analyze the problem. The way I am going to analyze it is I am going to say that this right here is my initial scenario, And I'm going to leave that as my initial, and that is an I standing for initial. I'm going to leave that as my initial scenario for the rest of the problem. So at point C, we're going to have gravitational potential energy, we're going to have kinetic energy, but if we're using this position as my initial scenario, then the internal energy is going to be all of the internal energy between A and C. So it's going to be E int AC, and let me get rid of that. And we're going to do the same type of thing for point D. So at point D, we have gravitational potential energy, we have kinetic energy, and we have internal energy. And again, it's the entire internal energy along the whole path. So we want to just start by finding the speed at point B. So we're going to set the initial GPEA plus KEA equal to the final scenario, which is KEB plus E int AB. What would this internal energy be? Well, remember, it's just going to be the work done by friction, specifically the work done by friction between points A and B, and that'll just be the frictional force times the distance. What is the frictional force? Well, I tell you specifically in the problem that the frictional force is equal to 1/5 its weight. So that's going to be 1/5 times mg. Now, this is sort of just a number I made up. They sometimes do this in textbooks to make the problem a bit easier to solve. They'll just say the friction is equal to 1/3 of the car's weight, or 1/2 of its weight. So I just kind of randomly chose 1/5 for this problem. It's not a rule that it has to be this fraction. Again, it's random. So the force due to friction is 1/5 mg, and it'll be times that distance. So let's go ahead and plug in the other formulas we know. So we know GPE is mgh, and kinetic energy is 1/2 mv squared. I've got all my subscripts there. And this is nice because all of these m's will cancel because there is an m in every term. And we can go ahead and plug in our numbers. So G is 9.8, HA is 35, VA is 7, VB is what we're looking for, G is 9.8, and then the distance from A to B is 55. So I gave that to you in the description of the problem as well. So you can go ahead and keep solving that. And I'm going to continue solving this problem on the next slide. So remember that the distance between B and C is 30, and C and D is 22. So from this point, we're going to subtract 107.8 from both sides, and then we multiply both sides by 2 and take the square root of both sides, and we get that VB is equal to 22.79. So by the time the roller coaster gets to here, it'll have a speed of 22.79 meters per second. Okay, now we have to find the speed at point C. So again, I am going to set this as my initial scenario, and this time, this is my final scenario. So we have GPEA plus KEA equals GPEC plus KEC plus E int, and then it's the internal energy all the way from A to C, again because I'm counting this A point as my initial scenario. And the internal energy will be equal to the work done by friction between A and C, and that'll be the force due to friction times the distance between A and C. Remember, this distance was equal to 55, and then this distance was equal to 30. So you just have to add those two together eventually. So the internal energy is going to be 1/5 mg dAc. Again, We get to this point, plugging in the formulas that we know, and we can cancel out all of the m's. We can plug in other numbers that we know. And I'm actually going to take this shortcut here. I know that this number is just equal to this, so I'm going to go ahead and take that little shortcut. And then I knew that G is 9.8, HC is 20, VC is what I'm looking for. And as I was saying earlier, the distance between A and C is 55 plus 30, which is 85. If you go ahead and keep solving that, you should get that VC is equal to 3.13 meters per second. Okay, last part of the problem, we want to find the speed at point D. So again, using this as my initial, but this time I'm using D as my final scenario. And forgot to change the subscripts here, but I'll just change them by hand real quick, so that should be all D's there. So the internal energy between A and D is going to be the work done by friction from A to D, which is that force, times the distance between A and D. And again, that's just 1/5 mg dAd. So here we've got this. All of these m's will cancel. And again, I'm going to use my shortcut here. I know that when I plug in the numbers here on the left side, I'm going to end up with that 367.5. And then on this side, G is 9.8. The height at D is 6. VD is what I'm looking for. And then G is 9.8. Then the distance between A and D, well, we have to add all of those distances that I gave you on the previous slide. So from A to B, it's 55. From B to C, it's 30. And then from C to D, it's 22. So if you add all of those numbers, you'll get that this distance is 107 meters. So then we can go ahead and just keep solving for a missing variable, VD. And if you solve for VD, you should get 14.07 meters per second. So hopefully you know how to solve conservation of energy problems with friction.